I'm going to be talking about one-dimensional sheaves, purity, and semi-simplicity of monodromy. Okay, so I'll just get started. So later, Magnus, I think, is going to prove purity for real sheaves, at least. I don't know exactly what he's going to do, but he's going to prove purity for some class of sheaves, and the proof of purity will depend ultimately upon reduction to the one-dimensional case. So what you do is you start with an arbitrary Lis QL bar sheaf of rank R, and you take its determinant, and by understanding the determinant well, you'll try to understand the sheaf F itself. Okay, so in the present lecture, what I'm going to do is I'm going to carefully analyze rank 1 sheaves, right? So that's the same thing as characters of the étale fundamental group. Actually, we'll consider characters of the Weil group, okay? But just in case, just to clarify notation, I don't know what notation you've been using so far. I'm just going to give some definitions here. So X will be a finite type geometrically connected K scheme. K will be a finite field of characteristic P. X bar denotes the extension of scalars to the algebraic closure, and little x bar is a geometric point of X. Okay, so then we have the canonical isomorphism between the Galois group of K and Z hat via Frobenius. And you have the subgroup Z generated just, instead of topologically, just generated as a group by Frobenius. And then the Weil group is just defined to be the preimage of Z, right? So you have this exact sequence. Here's the geometric fundamental group. Here's the full fundamental group of X. Here's the Galois group. The preimage of Z is the Weil group of X. Okay. So a Lis Weil sheaf, or Weil QL bar sheaf, is defined to be a finite dimensional continuous QL bar representation of the Weil group, okay? And you can give this alternative, somewhat, I guess you could say, more natural definition in terms of actual sheaves, which is just you have a sheaf on the algebraic closure, on X based into the algebraic closure, together with an isomorphism of this sheaf with its Frobenius pullback, where this Frobenius is the one on X obtained via the one on K bar. Okay, we'll never use that definition. Everything will be in terms of representations. Okay. By the way, if there are any questions at any point, feel free to just interrupt me. Don't worry about it. You don't have to go in the chat or raise your hand or whatever. Okay, so now the key to understanding one-dimensional sheaves, which is to say characters of the Weil group, and therefore it sort of underlies everything that will come later, is that any one-dimensional Weil sheaf basically has, not quite, but almost has trivial geometric monodromy. Okay, so we have the following result, which is really the main result of this lecture. I guess you'd say two main results, but this really is, I would say, the main result. So let K be a finite field as usual, X a normal geometrically connected K scheme of finite type. Then for any continuous character from the Weil group of X to QL bar cross, the restriction of this character to the geometric fundamental group, so extend scalars to K bar, actually has finite image. Okay, so in other words, like any character of the Weil group is almost trivial on the geometric fundamental group. And this immediately gives you purity of one-dimensional sheaves, because it tells you that the image of an element of the Weil group, up to roots of unity at least, only depends on the degree of W. So that tells you, if you look at a closed point X of your scheme, variety, whatever X, then the Frobenius at X, the weight of the Frobenius, the sort of absolute value of its eigenvalues, depends only upon the degree of the Frobenius, right? So that tells you that you have purity. Okay? All right. So now in Kiel and Weisbauer, yeah, sorry.
Can you repeat, please, what the argument for why it involves, why it gives you purity?
Sure. Yeah, so what does purity say, right? Purity says that if I take, so let's say to be pure of weight like beta, right? Be pure of weight beta means that if I take any closed point and I take its Frobenius, then the eigenvalues all have absolute value q to the beta over 2 under any complex embedding. Okay, so so that'll be true for some beta. Why is that true for, okay, on an irreducible piece, let's say, that'll be, actually for characters, it'll just be true, okay? So why is that true? Because if you take Frobenius, it acts so it's a character, so just some number, right, some scalar. And what is that scalar? Well, this theorem 1 here tells you that it only depends on the degree of your Frobenius, because it says that if you restrict to geometric monodromy, the degree 0 stuff, right? You have the Weil group, right? You have this exact sequence. The Weil group maps to Z. The kernel of that degree map is geometric Frobenius, right? Can everyone see my screen, by the way, like with my mouse moves and everything? Okay, great.
Yeah.
So, okay, so the degree 0 stuff, the geometric fundamental group, is pretty much killed by your character. It's mapped to roots of unity. So it's mapped to stuff of absolute value 1.
Mm-hmm.
So the absolute value of something only depends on its degree,
Mm-hmm.
which is exactly, I mean, in effect, what purity says.
Okay, cool.
Okay, is that good?
Yeah, I think I got the gist of it.
Okay. All right. So now I'll go to the proof. So I'm going to give a proof.
I'm terribly sorry. I didn't understand.
Okay, sorry. Okay, I'll do it again. So let's see. Actually, maybe I can draw here or something. Let's see. New share, whiteboard. Okay, we'll see how this goes. This probably won't go well, but let me try this. Okay, so let's see. Can I draw with this? So I have. So what does purity say, right? So to be pure. Well, this is not going to look good, but whatever. Okay, so that means that for any x in my scheme, big X, any closed point, the Frobenius at x,
Mm-hmm.
so you have the Frobenius at x, okay, so I have the Frobenius at x acting on this vector space V, right?
Mm-hmm.
Which is just a, well, in this case, just QL bar. Yeah, I guess this doesn't give it to you for cohomology, but it gives it to you for, okay, I guess I should have said what I meant by purity here. Yeah, that was, okay. Notions of purity, there's acting on the cohomology, and then there's just purity acting on the associated representation. So that's what I meant. So what I mean is you have Frobenius acting on this QL bar, right, via this character chi. And I want to say that the absolute value of Frobenius, by which I mean, okay, so what do I really mean? I mean, choose, embedding of this into the complex numbers, and then I mean the absolute value of tau of Frobenius. Okay? So I'm saying the absolute value of Frobenius should be Q is the size of your finite field, to the beta over 2, for some beta. There's some beta such that for all x this holds. So this is for all x.
Yeah, we want it to be the same for all x.
Exactly, that's the point. We want it to be the
but
same.
Why is this true?
Yes, okay. So the absolute value of Frobenius. So the point is that, does this go down? The point is that
You're saying the action of the fundamental group will move me from one point to another? That's the thing?
No, what I'm saying, no, the point is that the absolute value of an element of the Weil group, so I have a character, right? And the absolute value of an element of the Weil group is going to be what? Well, the character chi restricted to degree 0 stuff is roots of unity. Degree 0 is roots of unity. That's exactly what that theorem says. It says that if you restrict to geometric monodromy, you get roots of unity, right?
Yes.
Blah, blah, blah. Okay, roots of unity. So that means the absolute value of an element of the Weil group is going to be, well, let's say that chi of, so just choose an arbitrary element of positive degree, say sigma of degree 1.
Yep. May I suggest something?
Yeah, sure.
So it will depend only on the degree.
I think the thing that is maybe people are missing is that the point gives you a section from the Weil group back to the big group, and that's how you compute the.
I mean, I don't think you really need that, right? Because the only point is, I mean, what does this say? This says
I think that's what I'm missing.
But I mean, you don't actually need that. The point is chi restricted to degree 0 is just roots of unity, right? So
yeah,
that
but
means
what is the connection between x and w? That's what I don't understand.
X, and w. Oh yeah, so the point is w here is the Frobenius at x. That's the point. Sorry.
That's what Tomer said. Like, I think that the missing part was that how to relate the Frobenius at the point x to the Weil group and of x. What Tomer said is that a point.
Oh, I see. Oh, I see.
Section which gives you
okay, yes. No, you're right, Tom. Yeah,
what? Right. Can you say it? I didn't hear.
Yes.
Yeah.
So okay. So given your x, you get a section of the Weil group. Although, yeah, okay, fine. Given your point x, you get a section to the Weil group of big X, and then that gives you an element of degree equal to the degree of x. That's the point. The point is the Frobenius at x gives you an element of the Weil group of degree equal to the degree at x.
How does this correspondence work?
Okay, so let me maybe imagine.
If it's too long, I can. It's fine.
No,
I
it's
think
fine.
that
It's fine. I think we have time.
I think the easiest thing to say. Sorry.
If x is sorry, go ahead. You were going to say something.
I just think there is a short, easy thing to say. Like you have a map from X to spec FQ, and
Yeah.
an FQ point, at least, is just a section of this map. Now, everything is functorial. The fundamental groups, the Weil groups, the Frobenius, everything is functorial. So you see that, like, to get the Frobenius
Yes.
on the chosen point is to just evaluate
Thank
the
you.
section. In this.
That's
So
really
just one point. If you consider an FQ to the D point, then you have a map from spec FQ to the D to spec FQ, and you take a section of that on the Weil group. It corresponds to the multiplication by D map from Z to C, which is precisely the degree. So everything is compatible.
Okay, thanks. Yeah, sorry about that. I should have made that clear. Okay, is it good now? Maybe I'll just summarize in case someone just, okay. So the point is a rational point X or a rational point over some extension field gives you a section via functoriality of pi1, gives you a section to the Weil group from the Galois group of K bar over K. And that section is your Frobenius element, and its degree is the degree of X. And so, this theorem tells you that the absolute value of your character on a point W depends only on the degree of W. And so it depends only on the degree of your Frobenius, which is the degree of X, which is exactly what we want. So this is q to the beta deg X over 2. Okay? Okay, cool. Let's see now. So am I sharing now? Share preview. Okay, great. Okay. So at any rate, the point is this theorem 1 gives you purity for one-dimensional sheaves. It also gives you other things, which we'll do later in the lecture. I have till 10:30, right? Or, sorry, not 10:30. What is it there, 5:30? Yeah, okay. All right. Okay, so now let's begin the proof of this theorem. So I should say, because I think Kiel and Weissauer that's the reference I used for this lecture. And I don't know, maybe one of you can, I won't talk about it now because there's not time, but it seems to me that their reduction from the higher dimensional case to the case of curves is just doesn't work. I mean, there's even some argument they give later of some Bertini type result, which suggests that that their argument they give for the proof of this theorem 1 doesn't really work. So at any rate, I'm going to give a different proof, which also has the advantage of eliminating one of the cases in their argument. Okay, so it'll be a little simpler in that sense. Okay, so we start with some observations. So first, continuity of chi implies that okay, recall that chi was a continuous character from the Weil group of X to QL bar across. Okay, so continuity of chi means that chi factors through some finite subfield of some finite extension of QL lying inside QL bar. Okay, so that's because the Weil group is locally compact, right? It's an extension of Z by the geometric fundamental group, which is a compact group. So it's locally compact, so its image is also locally compact. And it's a fact that if you have a locally compact subgroup, then it actually lies in some such finite extension E, okay? So it actually lives in some E cross. And now we also note that E contains only finitely many roots of unity. So I don't actually know how comfortable people are with L-adic numbers. So I'll just, maybe all of you already know this, but I'll just say it just
I think
in
it's a
case.
good idea to say.
Okay. So E contains only finitely many roots of unity. Okay, so why is that? So you have the logarithm map, right? So remember you have this, you define by the usual series, what is it? Negative log 1 minus x is some x to the n over n. So that converges in some neighborhood of well, the way I've said it's 0, but the point is the logarithm converges in some neighborhood of 1. So it has an inverse, the exponential map going the other direction. So that gives you an isomorphism between an open subgroup of E cross and an open subgroup of the additive group E, right? So logarithm takes from E cross to E, and the exponential goes from E to E cross, just like with the real numbers. Okay, now E is a torsion-free group, right? The additive group E, it's E's characteristic 0, so it's torsion-free. And therefore, any root of unity, so pulling back to U, we see that U must be torsion-free. So in other words, any root of unity in U is actually just 1, okay? So now, why is it true that any root of unity, that there are finitely many roots of unity? Well, the point is that if I have a root of unity, there's an integer m such that, so here I say it here, there's an integer m depending only on E such that z to the m is U, and therefore z to the m is 1. Okay, so why is that? Well, if I have a root of unity and here's a uniformizer pi, then z to the size of the residue field is 1 mod pi, right? That's just, I don't know, algebra or whatever, right? So what is it, Fermat's little theorem? At any rate, z to the r is 1 mod pi, okay? Where r is the size of the residue field. And then there's a little piece of elementary number theory, which, because we're in characteristic L, this residue field is characteristic L, it tells you that when you raise to the L to the n, you get actually something that's 1 mod pi to the n plus 1. So each time you raise to the L, you get something that's closer to 1. And in particular, if you take n sufficiently large, depending only upon E, then you live in this subgroup U, right? You're close to 1, and therefore you're in the open subgroup U. Okay, so z to the m is in U for some m, and therefore z to the m is 1. Okay, so E only has finitely many roots of unity. And so because the character lands in E, which has only finitely many roots of unity, in order to show it as finite image on the geometric fundamental group, we only need to show that the image is torsion. Okay, if it's torsion, it lands in the roots of unity, so it's finite. Okay, so the key case is when X is a smooth curve. Everything comes from there. And in this case, the result is a consequence of class field theory for function fields. Okay, so I don't know how much people know about class field theory, but class field theory for number fields, there's an analog for function fields, which is very similar. Okay, so what you do is you let K be the function field of your smooth curve X, and XC the regular compactification of X. Okay, and so we recall the idels of K, not the idels, the idels are defined to be the set of elements of this infinite product of multiplicative groups that are almost everywhere units. Okay, so the product here is over all closed points of this compact curve XC, this proper curve. KV is the completion of K at such a point, which is the same thing as, okay, actually, this isn't quite correct. The completion of the local ring, you then take the fraction field. Okay, so it's the fraction field of the completion of the local ring at V, and it's the analog for function fields of the ring QP, which is the completion of Z at the closed point P, take fraction fields. And OV is, as usual, the ring of integers of KV. So OV is like ZP. Okay, but of course it's characteristic P here. So class field theory gives you an isomorphism between the Abelianized Galois group of K and the so-called idel class group. So you take the idels and you quotient by the principal idels, which are the ones where all these AVs are just A for some A and K cross. So you, like if I have the element 3 in K cross, then it goes to 3, 3, 3, 3, 3, 3, 3. So I take this quotient, this is the idel class group, and now I complete it. So I take the profinite completion. So this is just like in for number fields. For number fields, you have the same sort of isomorphism. The idel take the profinite completion of the idel class group. That's the Abelianized Galois group. Okay, so profinite completion in this case is actually sort of not very serious in the function field setting because, well, let me explain why. So you have a homomorphism from the idels to the group of V divisors on XC. Okay, so recall the idels are this infinite product, and you would have an element of the infinite product. Where does it go? You sum over all places V, over all local, overall closed points V, of V times the order of AV at V. Okay, so in other words, if AV is like pi square times a unit, where pi is a uniformizer at V, then this order is 2. So 2 times V. Okay. If anything is not clear, just interrupt me. Okay. So elements of K cross then map via this homomorphism to principal divisors, just by definition. A principal divisor is the divisor of an element of K cross. And so you get a map from the Idel class group to the Picard group, right? Picard group of X, C is just the divisors mod the principal ones. Okay. And now you have the usual degree map from the Picard group to Z, right? You have a line bundle, you can take its degree, or equivalently, you have a divisor, you take its degree, and thereby you get a surjective degree map from, so you take the Idel class group to pick, and then the degree map to Z. Yeah. Actually, the truth is, I don't know why I said this was, well, okay. Right. So I shouldn't have actually said that this is surjective. That's not, I'm not sure it generally is surjective. Maybe it is. Okay. At any rate, whatever. So you get so this degree map is compatible with the degree map from the Galois group of K bar Z hat to the Galois group of little K bar over K. And the kernel of this map is a profinite group. The kernel of this degree map is a profinite group because the Galois group is profinite, and this is just a closed subgroup. So all profinite completion does to the Idel class group is to replace the Z with a Z hat, right? The Idel class group maps to Z, the Abelianized Galois group maps to Z hat. Profinite completion just, their kernels are, the kernel here is profinite. So profinite completion just replaces the Z with the Z hat. This isn't such an important point, but okay. The point of the ultimate point of all this, which is why this all works, is the Abelianization of the Weil group is what? So the Abelianized Galois group is this Idel class group. If you take the Weil group, you take the quotient of this Abelianized Galois group, or actually the sort of Weil group, which is the unprofinite completed thing, where instead of Z hat you have Z. You take the quotient corresponding to the maximal abelian extension unramified over every closed point of X, right? The Weil group is, or if you think of, say, the fundamental group, what you're doing is you're taking the elements, you're taking the quotient of the Galois group by the quotient corresponding to the maximal everywhere unramified extension. That's what it is to be étal. To be étal means you're everywhere unramified. Okay? So the Weil group is just the quotient of the Idel class group corresponding to the maximal abelian extension unramified over every closed point of X inside XC. Okay. Now, when is something unramified at V? So the answer is given by local class field theory. So local class field theory says that at a place V, so to be unramified at V means exactly that you kill the group of units at V, right? So remember the Idels have this product thing. You have the units sit inside here as one of the products, right? You have one everywhere else and OV cross in the V place. And to be unramified at V exactly means you kill those units, okay? So the Abelianized Weil group then is just, you take the Idel class group and you quotient by, probably should have put parentheses here, you quotient by the product over all closed points of X of the units at V, okay? So this is the Abelianized Weil group. Okay, and so now we're in business because now we just have something concrete and we can, or relatively concrete, certainly more concrete than just saying the Weil group, and we can ask if any L-adic character of this is torsion. All right, its restriction to the geometric fundamental group is torsion. So remember, the geometric...
This turns out to be like a multiplication.
Sorry, what?
I'm confused about why you took why is this the product of these groups? Because like...
Sorry. The product, I should have put parentheses around this big product.
Ah, okay.
Sorry,
I didn't understand what you said. Okay.
Yeah, sorry, I'll add them in after that. I should have put parentheses. So it's
no problem.
Quotient by the product.
Mm-hmm. Cool.
Okay, and then you have, remember, this degree map to Z, and the geometric fundamental group is just the degree 0 stuff.
Just to make sure we're on the same page. So the reason you even consider the Abelianization is because you consider like one-dimensional.
Yes. So right. Yeah. So when I consider a character factors through the Abelianization. Right. So if I have a character of just any group G, then because the image is commutative, right? I'm going to QL bar cross. That's a commutative group. I factor through the Abelianization. Yeah.
Great.
Thanks. Right, and so now I want to show that the image of the degree 0 stuff in here is finite, or is torsion. Well, I consider this exact sequence. So I have the degree 0 stuff in here, right? The degree map factors through the unit. Right? A unit just maps to maps to the divisor 0, because the order of a unit is 0. So this thing is in the degree 0 part. I take the quotient. I have considered degree 0. I map to the corresponding degree 0 element where I quotient by all the unit groups, not just the ones in X. And then the kernel of that is the product over all points in XC minus X of the units. Okay? And so to show that this has finite image, it suffices to show that continuous character from here has finite image and one from here has finite image. Okay? So let's first consider the left side, or the left part. So we need to show that each of the elements, this is a finite product, and we want to show each of the elements OV cross has, for a character from OV cross to E cross has finite image. And the reason for this basically is because, I'll give somewhat more detail, but the reason basically is OV cross is basically a pro-P group, whereas E cross is basically a pro-L group. And so a continuous map from a pro-P group to a pro-L group, the image, it just has to be trivial. It's not literally pro-P, but it's basically pro-P. So I'll just give a little more detail now. So OV cross, it's not literally pro-P. What it is, it's an extension of a finite group by a pro-P group. Actually, it's even a product, but whatever. And so why is that? Well, here's a finite index subgroup. You take the set of elements that are congruent to 1 mod pi, mod a uniformizer, or absolute x minus 1 is less than 1. This is actually pro-P. And the reason, it's sort of similar to a calculation we did before. If pi is a uniformizer at V, then for x in this group, if x is congruent to 1 mod pi, then x to the p to the n is 1 mod pi to the n plus 1. So each time you raise to the p, you get closer to 1. And therefore, x to the p to the n tends to 1. So x was arbitrary, so this is pro-P. Okay. And similarly, O cross or E cross is basically pro-L. More precisely, if you look at the maximal compact subgroup of it, OE cross, the group of units, that contains a finite index pro-L subgroup. And that is, why is that? That's because the logarithm, once again, you have an open subgroup of this that maps isomorphically via the logarithm to an open subgroup of the additive group E, which is pro-L. Or OE rather, OE, the additive group OE is pro-L. Okay? So the logarithm shows that this OE cross is pretty much pro-L. So therefore, any continuous character from this product, this is a finite product of OV crosses to E cross, has finite image. So that deals with this left term. Is that good?
Yeah, I think I got the.
Sorry, I don't understand. So on the left, you have an infinite product, or
No, a finite
oh,
product.
that's a finite product. Okay, fine, sure.
Yes.
Thanks.
Although even if it were infinite, it wouldn't actually matter because the finite products times 1 everywhere else are dense in the infinite product. But yeah, it's
Okay.
actually a finite product. Okay. So, any other questions or? All right. Okay, and so now I just need to show that the image of this thing on the right, where I take the product over all closed points, not just the ones in X, has finite image. Okay, so why is that? So actually this group is finite. So that's why it's true. So why is it finite? Well, you have the map to the Picard group of XC as discussed earlier. And via that map, you actually get an isomorphism from this to the pic not. So just maybe sort of quickly say why that is. So let's go back to this pic, right? So you have the idels mod k cross maps to pic, and degrees correspond. So degree 0 goes to degree 0. The map is surjective pretty much by definition. A divisor is something of this form. Okay, although really what we need is injectivity when you quotient by the unit. So suppose I have an idel that maps to the trivial element of pic. That means that the divisor is principal. So if I change my element of k cross, I can assume it goes to the trivial divisor. And to go to the trivial divisor means all these orders are 0, which is to say all the AVs are units. So the kernel of this is just the product of the units. So it's exact. So we have this isomorphism.
Wait, so what's pick 0?
Pick 0. So you have pick of a curve, right? And you have the degree 0 elements. That's pick 0.
Okay.
Right? Like if I look at like
the
P1.
total degree, like you have the map to Z and the kernel.
Yes, it's the kernel that map.
Okay.
Yeah. Like if I look at P1, right? Pick of P1 is Z and pick 0 is just 0.
But why would pick 0 be finite?
Yeah. So I'm about to say why it's finite.
Sorry.
So the point is, this is a curve over a finite field. And so why is this finite? So it's actually just the points. So, okay, here's a general fact. If I have it doesn't really have to be smooth, but let's just say I have a smooth projective curve over any field whatsoever, then there is an abelian variety called the Jacobian of X, whose points exactly parameterize this pick 0. And so the elements of this pick 0 are exactly the k points. K, remember, is a finite field of the Jacobian of this thing. So it's just the k points of some variety over k. And k is a finite field, so any variety, finite type k scheme has finitely many points, rational points. So this is just the points of some abelian variety over k, so it's finite. And that completes the proof. Okay?
Great.
Cool. So, okay, now we do the dimension greater than 1 case. Yeah, so this is where Kiel and Weissauer, I think their argument goes sour. So the idea is just you slice X. I said slice by curves. I should have said slice. You slice X by linear spaces to get curves in X and to reduce to the curve case. Okay, so we just have some, this is always, I guess, how it works in étale cohomology, right? You just sort of you do something for curves, you can understand everything, and then you get a general thing by either slicing or fibering over lower dimensional things, right? That's how you do everything. So okay, now X is normal. That was one of our assumptions, and we really need that assumption. Maybe mentioned later. So for any non-empty open inside X containing X bar, whatever, the map on pi1s is surjective. So that's because, should I explain that, or I don't know if this was discussed in other talks, or, I mean, the idea is basically for normal schemes, the map even from pi1 of the generic point is surjective. And why is that? Well, when is a map on pi1 surjective? It's surjective exactly when, for a connected finite étale cover here, the pullback is still connected. And well, why is the pullback still connected? Well, because if I have y over x bar connected, right? Well, let's even pass all the way to generic points. To be connected over the generic point means precisely that y is irreducible. It means it has one generic point. Right, over the generic point, I have something étale, it's a product of fields. To say it's connected means there's one field. Okay, and so why if I have something connected over an étale over x bar, is it irreducible? Well, because since it's étale over x bar, which is normal, your cover is also normal, and if something is normal and connected, it must be irreducible. Basically, because if it were reducible, the connectedness means that two of the basically two of the components would meet somewhere, and at the point where they meet, you wouldn't have normality. That would be a bad point. Okay, so at any rate, for normal schemes and a non-empty open, the map on pi1s is surjective, so you can just, right, so if I have a character then of pi1, or actually I should have said the Weil group instead here, which is what we're considering. If I have a character and I want to show geometric monodromy as finite image, actually, I can say pi1. So if I want to show pi1 of x bar as finite image, it's enough to show pi1 of u bar as finite image because of the surjectivity. And so I can replace x by this open, and so assume that x is quasi-projective. Okay, and let's say it's a locally closed subscheme of Pn. All right? So now we have this lemma. So I consider the maps from pi1 of c bar.
Wait, is there like a theorem that a proper thing is generically quasi-projective or something like that? So, like what?
Yeah, well, okay. Suppose I have some arbitrary finite type thing, right?
It can be affine, so of course
right.
it can be finite. Yeah, sorry.
Okay. So if I consider the maps from pi1 of C bar to pi1 of X bar, as you vary over all smooth irreducible curves inside X bar containing little x, but this isn't so important, but whatever, then these maps are, the images of all these maps taken together are dense inside of pi1. Okay, so.
Do you need normality for this?
For lemma 2?
Yeah.
Yeah, I'm assuming I'm in this case. I should have said, but I'm still in this case, same notation.
I was
So
just interested in that, like, in that statement.
You're saying, do you need normality?
Yeah.
Yes, you do need normality. Yep.
Okay, but it's true for any normal variety, this statement?
Probably. I guess what you would need is just a normality. I mean, I don't know, is there a Bertini theorem for normality? Well, actually, I think
like
if
normally irreducible or something.
Yeah, if you're normal, you're smooth in codimension 1, right? Or something. So, or generically smooth in code, you're probably even smooth in codimension 1, right? So then I think yes. I mean, this is really a generic statement. I mean, the proof of this, I'll come to it after. I'll say how it finishes it. But the proof of this basically is you slice X by suitably general linear spaces. And so you just need to ask yourself, like, if I slice by a general thing, do I get normal curves? And if X is normal, I think the answer should be yes. Okay. Right, so we have this. So the images of maps from curves, of smooth irreducible curves in X, are dense in pi1. And so that basically finishes the proof, because if I take a curve as in the lemma, then it actually descends to some finite extension, k prime over k. And then I consider chi restricted to pi1, base change to k prime, or I should have actually said ve, not pi1, but whatever. Then the geometric fundamental group of C prime has image lying in the finite subgroup of roots of unity because of the curve case. And since these are dense inside the geometric fundamental group X, it follows that this group also maps into this finite group of roots of unity, because a dense collection of elements does. Right, because to map in the roots of unity means that you satisfy like x to the n is 1 for, there's some n, so that you satisfy x to the n is 1. There's a fixed n such that for all of them x to the n is 1, and that then if it's true on a dense thing, it's true everywhere. Okay, so just slicing by curves. Now, is that good? Okay, so let me go to this lemma. Yeah, and I just have this little remark. The condition that C bar contains X bar is irrelevant because you're taking characters, and when you pass the Abelianizations, base points become irrelevant, but whatever. Okay, so why is this true? So the point is, if I have a connected finite Galois cover with a fixed specified geometric point, then you want to show there's a smooth irreducible curve C, or C bar, inside of X bar, such containing little x bar, whatever, such that this composite map to the, so you have pi1, it surjects onto the automorphisms of y bar. This composite map is surjective. That's what I want to show. That's exactly the statement of, well, okay, it's not exactly. I guess what I would exactly would be for any element in this automorphism thing, there's a C. But at any rate, whatever, there's a pi1, there's a C such that this composite is surjective. That certainly suffices. Okay, and so surjectivity is just equivalent to the statement that the finite étale cover of C bar obtained via pullback, so you take y bar, pull it back to C bar, is connected. Okay, so now, unfortunately, I couldn't really find a reference. I'm sure there might be one. I'm sure there is one, but by a suitable version of Bertini's theorem for étale covers, there's a dense open subscheme of the Grassmannian of codimension dim x minus 1 linear subspaces of projective space, okay, such that for each element here, each element is u bar, if you take the intersection with x, so because the codimension is dim x minus 1, this intersection you expect to be a curve. And the point is that there's a version of Bertini's theorem which says that generically it's a smooth, irreducible curve such that this pullback is still connected. And that proves, and therefore the theorem.
Could you repeat that part again? It was very fast for me.
Sorry, go ahead. Were you going to say something?
I said maybe you didn't hear me. I said, could you repeat this part because it was very quick for me.
Oh,
like
sure,
the last argument.
Okay, so we want to get this map from pi1. So for a given y, we want to find a curve C so that this is surjective, right? And And so that's equivalent to saying that the pullback of this cover to C is connected still. Okay. So, well, okay, before I say the Bertini thing, if I consider a codimension dim x minus 1 linear subspace of projective space, right? And I intersect with x, you expect that it cuts the dimension down by dim x minus 1, so you get a curve probably, right? So you expect that at least if I take a sort of suitably general L, then this intersection's a curve. And even that it's smooth, using that x is smooth, and even that it's irreducible. And there's a Bertini, right? Standard Bertini theorem, I think, is the one that says this. It says that this will be a smooth irreducible curve. We want something a little better. We don't want just that's a smooth irreducible curve. We want that the pullback also of y to this curve is connected. So, you know, if you just had the pullback of x being connected, that's this irreducibility statement. But we want the pullback of y to be connected. And there is a version of Bertini's theorem for étale covers. In fact, I think the proof given in Hartshorn also proves it, but maybe I should look for a reference. I couldn't find it. But at any rate, a suitable version of Bertini's theorem, I mean, when you say Bertini's theorem, right, it's a very general sort of, I guess it's never really clear what you actually mean. It's some statement that if you take a suitably general linear space, then something good happens. And something good here is smooth irreducible curve such that this is connected.
I see, thanks.
Yep. Okay, and that proves the lemma, and therefore also the theorem. All right. Okay, so maybe I'll just talk this remark here. So I might go through this sort of quickly because I have to get to the other thing. But okay, so by slightly modifying the proof, you can obtain a version of this for generic points. So you consider the Weil group of the function field of your x, and then the restriction to the Galois, the sort of geometric part, which is to say the Galois group of k bar over little k bar k has finite image. Okay, so you can obtain a generic version of it. And also, I guess I'd say this condition that x be normal, I won't read all this, but the condition that x be normal is necessary. So here's an example. If you take the nodal cubic, then pi 1 of it is z hat. And if you're wondering, so the degree n cover of this thing, the degree n finite étale cover, is just a collection of, it's a polygon. You take np1s, arrange them cyclically, and each is glued to the next at some rational point. So that is a Galois cover, right? The normalization of this cubic is p1. And blah, 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 blah. So the point of all this is the Weil group is essentially, I'll skip some of this stuff, but if you can work out so that the Weil group is essentially z, is z times z hat. Okay? The z being the degree thing and the z hat being this pi 1 of this normal, of this nodal cubic. Okay, and in particular, right, there are certainly characters from here whose restriction to z hat is not trivial, is not finite image, right? Take like the character which, let's say, kills this z and sends 1 to whatever, sends 1 to like L, or sorry, 1 to, not L, 1 to something that's 1 mod L in E cross. So there are, so at any rate, the point is that normality is really essential here. Okay. Right. So the second main result of this talk is Grothendieck's theorem on semi-simplicity of the geometric monodromy associated to a Lie sheaf. Okay, so semi-simplicity, what is, so, okay. Semi-simplicity of here means in the sense of algebraic groups, and semi-simplicity of an algebraic group is a statement about the non-existence of certain algebraic characters. So given that you want to say some character doesn't exist, non-trivial character, it's not surprising maybe, I mean, I'm not saying the proof is trivial, but it's not surprising that the theorem is really ultimately a consequence of the above result, which says basically that there are no interesting characters in geometric fundamental group. Okay. So first, let's now define the monodromy group associated to a Weil sheaf. So let X be a geometrically connected K scheme. And let F be a Lie Weil sheaf, QL bar sheaf, and you have the associated representation. So your V is a finite dimensional QL bar vector space, and rho is continuous homomorphism. So the geometric monodromy group of F is, by definition, the Zariski closure. So you have, okay, this is wrong. I don't know why I wrote this. It's the Zariski closure of the geometric fundamental. This is wrong. This should be geometric fundamental group, not the Weil group. Okay, that's why geometric.
Pi 1 x bar.
yes, I want pi1 of x bar. That's right. Yeah, so you take the image of pi1 of x bar, and you take this risky closure. Okay, so that's some closed subgroup of GL of V, right, of some GLN over QL bar. Okay, that's just a definition. And now choose a section of the Weil group. Choose a section from the Weil group of K bar to the Weil group of X. So that is nothing more than an element of degree 1 inside this group. That's what a section is. And then via rho, you obtain an action of, so via using this section and then using rho maps the Weil group to GL of V. And so you obtain an action of the Weil group on the geometric fundamental group by conjugation, right? The Weil group acts on the geometric fundamental group by conjugation. And so you then obtain via the section action of this Weil group of K bar, which is just Z. And so now the arithmetic monodromy group instead of geometric associated to the section is this group. It's the group you take the semi-direct product of this Weil group of K bar over K, which is just Z, on the geometric fundamental group. Okay. And this is an algebraic group. It's locally of finite type. Its identity component is this, is the identity component of this geometric monodromy group. Okay. Okay. So now here's the theorem. Let X be a normal geometrically connected K scheme, and F a geometrically semi-simple Weil sheaf. And unfortunately, the word semi-simple here is sort of overloaded. Semi-simple here, of course, just means in the sense that the representation is semi-simple. And then semi-simple here, so the first statement, the algebraic group G, the geometric monodromy group is semi-simple in the sense of algebraic groups. It's a semi-simple algebraic group. Okay. And now the second condition is if Z is the center of this algebraic group G, which contains this geometric monodromy group, it's the center of the arithmetic monodromy group, then the map from Z, the degree map from here to the Weil group, which is just the integers, has finite kernel and co-kernel. So, okay. And in particular, to say it's finite co-kernel, in fact, exactly says the center contains an element of positive degree. Okay? Does the statement clear? Okay. So now, okay, so let me turn to the proof of semi-simplicity. So, okay. First of all, make it a little reduction. So you can replace X by a finite étale cover. That just replaces the fundamental group by the étale fundamental group or the Weil group by a finite index subgroup. And in particular has no effect on the identity component of this geometric monodromy group. And by making a suitable such cover in order to just land inside the identity component, you can assume that the geometric monodromy is connected. Okay. And I should also mention, finite étale cover, you can also—
Why is that?
Why can you assume it's connected?
No, like why is replacing by a finite étale cover doesn't affect the identity component?
Yeah, well, the reason is so that gives you a finite index subgroup, right, of the fundamental group. Like if you think of fields, right? If I replace a field by a finite extension, the corresponding Galois group's a finite index subgroup.
Okay.
And so if I replace by finite index subgroup, then what I'm getting is if I take Zariski closures, I'm going to get a finite index subgroup of a connected group then, when I restrict identity components. And the finite index thing there is just the whole thing.
Cool. Thanks.
Yep. Okay, so we can assume it's connected, and in particular, an example of a finite étale cover is extending scalars on K. So you can replace K by finite extension. We'll use that later. Okay. So we first check that the geometric monodromy group is reductive, right? So to be semi-simple, what does it mean to be semi-simple? It means you're reductive, and a bunch of equivalent definitions. Well, okay. I'll give the definition of semi-simple when we come to it. But one of the conditions to be semi-simple, you in particular have to be reductive. Okay. And this is a totally general fact having nothing to do with our particular situation. Any algebraic group over QL bar which admits a faithful, okay, I should have said locally finite or finite type, whatever, finite type. Well, I guess algebraic group means finite type, whatever. So admitting a faithful semi-simple finite dimensional representation is reductive. And actually, there's nothing special about QL bar either. It's QL bar replaced by any perfect field. The same thing is true. Okay, so why is that? We need to show that if I have a normal, smooth connected, unipotent subgroup of this group H, which I want to show is reductive, then it's trivial. That's what it means to be reductive, essentially. Well, over QL bar, that is what it means. For each irreducible subrepresentation of V, the Lee-Colchin theorem says that the space of U invariance is not zero. Okay? So normality of U tells you that the space of U invariance is actually an H invariant subrepresentation. It's an H invariant subspace of W. Okay? That follows from normality. And therefore, because it's an H invariant subrepresentation of this irreducible W, it must WU must equal W, just by irreducibility of W. And now V is the sum of its irreducible subrepresentations, so it's the sum of such W's, and therefore it follows that VU is V. Okay, which is to say U acts trivially on the representation V. But the representation is faithful. So if U acts trivially, it must be trivial. Okay. So this, we didn't really use anything specific to our situation. It's just, yeah, so it's a reductive group. Okay, now we have to prove semi-simplicity where there actually is something to show. So what does it mean to be semi-simple? So for a reductive group to be semi-simple means that it has, let's say connected reductive, means that it has no non-trivial.
Zev?
Sorry, yeah.
What is the discussed representation?
What is this? What representation?
Like you said, okay,
Oh,
it's
sorry,
reductive because it has a representation, a semi-simple one, right?
Yeah. So the geometric monodromy group, by definition, is a subgroup of this GL of V. So the representation is
yes. Oh,
so
sorry, yeah, of course.
And it's semi-simple because of our assumption that F is geometrically semi-simple. So it's a semi-simple representation. Okay, I should have specified that. Okay, so now for semi-simplicity, well, okay, so we'll first show that G contains a central element of positive degree. Okay, so let zeta be an element of degree 1. And then, okay, so now we use the following important fact about reductive groups. So any automorphism of connected reductive group is the product of an inner automorphism and an automorphism of finite order. This is a fact about reductive groups. In fact, the outer automorphism group is the automorphisms of the Dinkin diagram. So it's a finite group. So there exists an element in the geometric monodromy group such that conjugation by, well, okay, such that conjugation by G zeta is an automorphism of finite order, right? Because the conjugation by zeta is the product of conjugation by some G and an automorphism of finite order. I guess here I want G inverse in order for it to be G zeta. The point is, though, if you modify it by an inner automorphism, which is to say you multiply by a suitable G, then conjugation is of finite order. Okay, so this element Z is degree 1, and Z to the n for some positive integer n is therefore its conjugation action is trivial. So it's an element of G of QL bar of degree n, which centralizes the geometric fundamental group, which is what we wanted. Yeah. Well, actually,
I didn't understand the last step. Like you meant to take n, which is the finite order.
Yes.
Okay.
But could Z to the n be trivial?
No, it's of degree n.
It is degree n. Yes.
So at any rate, replacing K by a degree n extension, we can assume that there's a degree 1 such element. So remember, we could replace K by finite extension. And so we get a splitting of G, right? A central element of degree 1, in fact, gives you a splitting like this. It tells you that the semi-direct product can be written as a product, okay? Well, it doesn't say that the other semi-direct product, but it says there is a presentation like this, where this is a splitting. So this is the sort of geometric model. Okay, now suppose for the sake of contradiction that the geometric monodromy group is not semi-simple, okay? Then, so, okay, what does it mean to not be semi-simple? It means, this is one equivalent definition, that there's a non-trivial homomorphism from this group to GM. Okay, this connected group, we assumed it was connected. Remember, we made some reduction. From this connected group to GM. So now, if you compose rho with projection onto the first factor in this decomposition, right? So that's a map from the Weil group to the geometric monodromy group, which restricted to geometric monodromy is the identity.
Why does that? Why does that is the same thing? Like being not semi-simple and having a map to GM?
Well, I guess it depends what your definition of semi-simple is.
Like what
Okay,
I know is like that it has a normal connected solvable subgroup.
okay, well, so a solvable subgroup, which is reductive, which, okay, the normality implies your subgroup is still reductive. And a solvable group that's reductive, at least over a solvable reductive group is just a torus. So you're saying that there's a normal torus, right? Because any solvable group over, let's say, a perfect field is a torus semi-direct, a unipotent. So if you're reductive, that unipotent. So you're just a torus. And a normal torus in a connected group is always connected finite type, is always central, because conjugation of the group on the torus yields a map from the group to the automorphism functor of the torus. And it's a fact that the automorphism functor of a torus is represented by an étale scheme. Like if you think of GM, the automorphism is Z mod 2. In general, GM to the n, you get GLN of Z. And then there's some Galois descent argument. For a general torus, you get an étale group scheme. So if I have a map from a connected thing to an étale thing, it must be constant. So that means that conjugation actually is trivial on the torus. So the torus is central. And if I have my central torus, then by, I guess you could say, the structure theory for reductive groups, right? A central torus means that there is a, means that G, well, basically, okay, G is the product of its derived group and a maximal central torus. And so the character is basically, the Abelianization of G is going to be then some non-trivial torus. And so that Abelianization gives you your map to GM. Okay. I should have said actually here, I'm using also the fact that QL bar is algebraically closed. But okay, I don't want to spend too much time on that. I mean, we can discuss it after if you want or something, but yeah, over an algebraically closed field, to not be semi-simple is exactly the same as saying that you have a non-trivial homomorphism to GM.
Cool. Thanks.
Connected. Yep.
Can you also construct this just by like restricting, like taking a character of the torus, restricting from the quotient map from a parabolic subgroup and inducing or something like this? This is the kind of character.
Well, I mean, I don't know. The way I know to construct it is just, it's what I basically just said. You have G, the Abelianization of G is always a torus. And yeah, I mean, the Abelianization of G is a torus, and to be semi-simple is exactly to say that G equals its derived group, which is to say the Abelianization is trivial. So the torus is trivial. So the way I would construct the characters, I'd say G to its Abelianization, that's a torus. You're over an algebraically closed field, so the torus is just a product of GMs, and so that gives you your character.
Okay, thanks.
Okay, so the composition, okay, so now I have this character, and so the composition of rho with projection onto the first factor in here. So I have the Weil group, I project to the first fact, I map to G via rho, and then I project to GGM, to this geometric monodromy group. That yields a continuous homomorphism from the Weil group to QL bar cross, right, to GM of QL bar, which is QL bar cross. And restriction to the geometric monodromy is exactly this character chi, which is, so it's a non-trivial character. So the restriction geometric fundamental group has Zariski dense image. It has infinite image. Zariski dense image in GM of QL bar. And that's that contradicts theorem 1. Theorem 1 says exactly that, so this image must be finite. Okay, and that proves 1. So that contradiction shows that, in fact, it is semi-simple. Okay. Yeah. Are there any questions about that? Okay. So now for part 2, it's sort of a little finicky stuff. It's kind of annoying. I mean, basically, we have to, the issue, we basically, okay, so part 2, let me recall what it says. So the map has finite kernel from the center of G, this full arithmetic monodromy group, has finite kernel and co-kernel. Okay. Well, first of all, the finiteness of the kernel is, so what is the kernel of this? Well, if you're in the kernel, you're in particular so that means you're degree 0, so you're in the geometric monodromy, and you're actually in the center of the geometric monodromy. And well, we just showed that that thing is semi-simple, which means that exactly says, in fact, that the center is finite. Okay, so this kernel is finite because the center of this semi-simple group is finite. So it only remains to show that Z contains an element of positive degree, right? That's the same as saying the co-kernel is finite, because this is just the integers. Okay. So the argument we gave in this proof 1 here, so remember we constructed this degree 1 element such that a power of it centralizes the geometric monodromy. And we didn't actually use connectedness for that, but that's just a general argument. Okay, remember using this fact that the outer any automorphism is a product of an inner and an automorphism of finite order. So we have an element of degree 1 such that a positive power of it centralizes. Okay, so we had to use, right, that if we have a connected reductive group, the automorphisms of it are inner times finite order. So we have to, so it only centralizes the identity component of the geometric monodromy now. Okay. So this is kind of what's so finicky about this part. You have to deal with the disconnectedness. So replacing zeta by zeta to the R for suitable R, we can also assume that conjugation by zeta is trivial on this geometric monodromy group. Well, sorry, it is trivial. We can assume it's trivial on this quotient group I meant. This is some finite étale group scheme, whatever. So we can assume that it's conjugation by it's trivial on this finite group of connected components. And now for G, so now we consider these weird maps. So for G in the geometric monodromy, we have the map phi G from Z to the identity component of geometric monodromy defined by this. So phi G of n is G zeta to the n, G inverse zeta to the negative n. And we want to show that there is some positive n such that phi G of n is 0 for all G in G, because that exactly says that zeta to the n centralizes G. Okay, so that'll tell you that zeta to the n, sorry, this should be G geom. So zeta to the n.
One? You mean 1? When you said 0, you mean?
Yeah, okay, I should have said 1, you're right. Yeah. Yeah, you're right, I should have said 1 really, because there's no, yeah. Okay, so phi G of n is trivial, let's put it that way. So that tells you that zeta to the n trivial or centralizes the geometric monodromy, okay? And if it centralizes geometric monodromy, well, then it centralizes everything because it centralizes zeta, remember, was a power of this degree 1 element Z. And so it centralizes a degree 1 element and the geometric monodromy. That means it centralizes the whole group. Okay, because the whole group is generated by those two groups. Okay, so now it's just a straightforward calculation to see that phi G defines a cocycle, okay, which is to say phi G of n plus m is phi G of n times n acting on the image of m, which is to say zeta to the n conjugating phi G of m. So this is just a calculation, doesn't really use anything. Okay, since zeta centralizes the identity component of the geometric monodromy, it follows that this map is, so this conjugation is trivial because this phi G lands in the identity component. So this is just conjugation does nothing. And so that exactly says that phi G is a homomorphism. Okay. So now we have these two identities, which are just, you just check them. So since zeta centralizes the identity component of geometric monodromy, you have these identities for all G in the geometric monodromy and G prime in the identity component of geometric monodromy. Okay? Okay, so what does this say? This says if I take G and change it on the left by, okay, so because the identity component is normal, this is just the set of elements in the geometric. As you vary over all G prime and identity component, this just varies over the whole identity component. And so this says that phi G is invariant if you replace G if you multiply G on the left by an element in the identity component. And this says that changing on the left by such an element corresponds to conjugating by the element. Okay, and so what does these two things together say? That phi G, it lands in the image of phi G is centralized by the identity component of geometric monodromy, right? Because if I centralize, that means I multiply on the left by this thing down here, and this says that does nothing. Okay, so that means that phi G lands in the center, and so the center here is finite. That's exactly right, because this is a semi-simple group, its center is finite. And so for some n greater than 0, phi G of n is trivial. For some n depending only on this group, not depending on G, phi G of n is trivial for all G in the geometric monodromy. Okay, and so that says that zeta to the n centralizes the geometric monodromy. Okay, and so replacing zeta to the n, we have an element of positive degree which centralizes the geometric monodromy, and this element was a power of a degree 1 element Z, which it therefore also centralizes, and so it centralizes the entirety of the group G. Okay, so that's a little sort of annoying, but okay, and that's that whole argument there. Let me just say, so I'll just briefly say why, because this just seems sort of random. Why do we care about this? So I think Magnus tomorrow is going to be talking about determinantal weights. And the point is, so okay, I won't say what a determinantal weight is, but let me just say that the point of this whole thing will be using an element of positive degree in the center. You'll be able to, if I have, let's say, an irreducible representation, then Schur's lemma says that a central element acts by a scalar on it. So this will say that there's an element of positive degree that acts by scalars. And so that'll tell you, so if I want to compute the weight of a sheaf, the way to compute weights is I take some Frobenius element and I just see what are the eigenvalues, right? And I ask what are the absolute value of the eigenvalues. And because of this statement earlier that for one-dimensional sheaves, that depends only on the degree, I can just choose some positive degree element and say, how does that act? What are the eigenvalues of that? And so I just choose a central positive degree element using this, and that central positive degree element acts as a scalar, because by Schur's lemma on an irreducible thing. And so you'll be able, and so, you know, scalars are easy to understand, their eigenvalues. So that'll allow you to understand weights by how weights behave basically under various operations like tensor product and exterior powers and so forth. So that's the utility, that's the point of this. It'll allow us to analyze weights by looking at elements which act as scalars on irreducible representations. Okay, so that's it, I guess. Yeah. So are there any?
I think we have a few minutes for questions, and then we'll move to the Q&A. So if anyone has any questions. Okay, if not, okay, go ahead.
I just, it's not really a question. It's like the thing that I wanted to happen if there are no questions. That is, if you can recall the theorem 1, like,
theorem 1,
and the exact way that we used it in the proof of the part 1 of the theorem 2.
Ah, the proof of this thing. Yeah. The proof of this. Yeah, so the way we used it was, okay, so down here. So remember, we obtained this splitting of the geometric, of the arithmetic monodromy group as a direct product like this. Okay, and so the point was, we want to show the geometric monodromy is semi-simple. To say it's not semi-simple exactly says that there's this non-trivial character. So this non-trivial character yields, so if I have an element, so if I have the Weil group, I can map it via rho, I have this representation. So that lands the Weil group inside G, and then I have this projection to this geometric monodromy, okay? So that yields then a splitting, right, of the corresponding splitting of the Weil group. Well, sorry, not of the Weil, of the image of the Weil group. But at any rate, that means if I restrict, so I have this map from the Weil group to the geometric monodromy, which restricted to geometric fundamental group is just rho, because this is a splitting. All right? And so now I compose with this character, and I get, via that, a map from the Weil group to QL bar cross. Such that restricted to the geometric fundamental group, it's, you know, take rho and then take this character. Now, rho has a risky dense image in here by definition. This is this risky closure of the geometric fundamental group. And chi is non-trivial, so it has a risky dense image, so the composition has a risky dense image. So in other words, that means I have this character such that restriction to the geometric fundamental group has the risky dense image inside QL bar cross. But theorem 1 says that if I have a character like this, then the restriction to the geometric fundamental group has finite image.
Yeah.
So this is a contradiction.
Cool. Thanks.
Any other questions or requests for clarification?
Maybe If you can repeat the last thing you said in your talk before answering the question about how do we use part 2 to control purity
Oh, yeah. Yeah. Okay. So actually, it's not really. I mean, okay, it's used in the proof of purity, but it's not so much. It's not really used so much for purity itself. I mean, it's important in the proof, but it's not used so much for purity itself as for understanding how weights behave under various. So, I mean, the way purity is going to be proved, let's say for real sheaves, is going to be you take some high tensor power of a sheaf, and you understand how the eigenvalues behave under this high tensor power. And so you'd like to understand how weights behave, what will be called determinantal weight. So a determinantal weight will be basically the weight associated to, I take a sheaf, I take its determinant, that's now a one-dimensional sheaf, right? The top exterior power. And that's because it's one-dimensional, it's pure by this thing I said earlier. So now it's like, okay, well, what are the weights of that, or effectively, not exactly, but roughly the weights of that are the determinantal weights. Okay, so we want to know how do the determinantal weights behave, which are like a poor man's version of actual weights, and then we'll somehow understand actual weights from the determinantal ones. And the point is, we'll have to understand how the determinant weights behave under various operations. And so it's like, well, how do you understand that? And the way you understand it is, we know how scalars behave under various operations, right? If I have a representation acting via multiplication by 2, if I have like an element which acts via multiplication by 2 on one representation, multiplication by 3 on another, then on their tensor product, it's multiplication by 6. Okay, stuff like that. So if I have a scalar, then I know how it behaves under various operations. And the point is that to compute the determinant weight, so on a one-dimensional representation, to compute the weight of an object, I just need to understand the weight of any positive degree element, right? Because of this theorem 1. That's the point of theorem 1. It says that the degree is all that matters. So I just take any positive degree element, possibly having nothing to do with Frobenius or anything. And so what I do is I take the one that's guaranteed by this. I take an element of positive degree that's central in this G. And since it's central on an irreducible representation, it acts by scalar. And so that'll tell us that we can use these scalars to understand how weights behave under various operations, how determinant weights behave. Yeah.
Great, thanks.
So I think Magnus will talk about that tomorrow.
Like in an actual specific situation, you will have to know the degree of the element, right? To actually compute, because it's up to like, if you want really to know the weight,
yeah.
Then if you take a positive degree, then you actually need to know the degree. But if you like do a theoretical, if you want only theoretical control, then it's probably enough. That's like,
yes, that's right. Okay. The thing is, we're not going to, like, so what you're going to do, right, is, yes, for theoretical things, you're just going to basically compute. You're going to say, you're not going to say, well, what is the weight? Especially, you can't really, right? You're just dealing with some general sheaf. But you're going to say, well, there is some weight because of this. And yeah, you're right, though. To actually compute it, I mean, that only tells it to you up to multiplication by some rational number. Yeah. Yeah.
Thanks.
So
really great talk.
Zev, again.